Hi AP Chemers. Today we're going to start chapters 3 and 4. So chapter 3 deals with chemical reactions, types of reactions, and chapter 4 deals with stoichiometry. Some good news is that predicting products is out of the AP exam. So they won't give you two reactants and tell you, hey, what products do they make? But they do expect you to be familiar with the types of products that they should make. They also expect you to know what type of reaction it is. They still expect you to be able to balance chemical reactions and answer some questions about these chemical reactions. Also, a long time ago, they used to make you memorize the solubility rules. That is no longer the case, except for one rule that you need to memorize. You need to memorize that sodium, potassium, ammonium, and nitrate salts are all soluble. So the exclusion statements are here to kind of keep those in mind. And also don't forget that these are your learning objectives, and so you kind of want to read through these, especially at the end of the chapter, to make sure that you understand every single one of those. So let's go ahead and get started with chapter 3, the chemical reactions. So let's take a look at an example of a reaction here. So we have solid ammonium dichromate yields chromium 3 oxide, nitrogen gas, and then gaseous water. So let's write out our chemical reaction that we see here. So ammonium dichromate, that's an ionic substance, which means that I need to be able to write a neutral compound. That is still on the AP exam. So ammonium is NH4 plus, dichromate is Cr2O7 2 minus. So ammonium dichromate is going to be NH4, 2 of those, Cr2O7. They tell us it's a solid, so we should know to put an S there. And then yields, so arrow, chromium 3 oxide. So chromium 3 means Cr3 plus, oxide is O2 minus, so Cr2O3. Nitrogen gas, so plus, nitrogen is N2, and they tell us it's a gas, so we put a G. And then also gaseous water, so H2O, and since it's gaseous, we'll put a G. They don't tell us what the chromium 3 oxide is. They don't tell us if it's a solid, liquid, or gas, but we know that it is, if it's at room temperature, it should be a solid, right? All ionic substances at room temperature are solids. You don't have to put that there because they don't really tell you, but this is just for our notes. Something is wrong with the reaction as written. We've lost mass as we go from the reactants to the products, which is not possible. And so that's why we need to balance our chemical reaction. And so if we put, let's see, a 4 here, that balances our chemical reaction. So what is conserved in a chemical reaction? How did I know to put the 4 right there? Well, I was trying to balance out the number of atoms, right? So number of atoms is conserved. We know mass is conserved, right? Probably energy as well. How about the number of moles? Is that conserved? It is not. Moles are not conserved. On the product side, I have just 1 mole. On the product side, I have 6 moles. Same thing with molecules or particles in general. The only particles that are conserved are the atoms, not molecules, not formula units, nothing like that. So just atoms and mass is conserved. All right, now most of our chemical reactions are done in aqueous solutions. So like I said, back in the day, you had to memorize all the solubility rules. If you remember last year, you had them on the back of your periodic table. That's no longer the case this year. You don't have them on the back of the periodic table, but that's okay because you only need to apply them. You do not need to memorize them, except for that one rule that says that all sodium, potassium, ammonium, and also nitrate salts are soluble, no exceptions. But if you were given something like this, you should be able to interpret it, right? So these are the soluble compounds. These would be the exceptions to them. These are the insoluble. Slightly soluble means insoluble, because really when we say insoluble, that means a very little amount of it dissolves. And this is the exception to it. And this exception actually applies to the whole thing here, whereas these exceptions only apply to what's next to them. So for example, these are soluble, no exception. These are soluble with these exceptions. These are soluble with this exception, and so on. So let's play soluble or insoluble. So we have PbCl2 first. And so I'm trying to get it so that it's, there we go, that's showing us the whole thing. Sorry, guys. There we go. Sorry about that. So PbCl2. Let's look through to see if we can find anything about lead. I don't see anything about lead much here, except for this and this. Oh, and this. So let's see, chlorides. This is a chloride. So chlorides are soluble except when they're with silver, mercury, or lead. So that means it's not soluble. Most chlorides are soluble except when we're these. So this would be slightly soluble or insoluble. I'm just going to put insoluble. Again, that means slightly soluble. All right, Na2SO4. Is there a rule for sodium? Yes, there is. It's a little bit higher here. That was one of the rules that you have to memorize. All salts of sodium are soluble, no exception. Now this one was sodium sulfate. If you look at sulfates, they are also soluble. They have some exceptions, but that's not the case here. So this is definitely soluble by both the sodium and the sulfate rules. Okay, how about aluminum phosphate? I don't see anything about aluminum. I do see something about phosphates here. So phosphates are not soluble unless they're with alkali metals or ammonium. Well, it's not with an alkali metal or ammonium here, so that tells us that it is slightly soluble or insoluble. Okay, and the last one, this is ammonium acetate. We know that everything with ammonium is soluble. Let's see, where's the rule? Right here. Everything with ammonium is soluble, no exceptions. Acetate is also soluble, no exceptions, so that is definitely soluble. All right. Next thing we want to talk about with reactions is that there are some substances that are considered electrolytes. Electrolytes mean that they basically have ions. They give ions when they're put in water, and because there are ions, that means positive and negative separated, and so you have the ability to conduct electricity. So electrolytes are substances that dissolve to give ions in water, and they conduct electricity. There are strong electrolytes, weak electrolytes, and also non-electrolytes. So let's start with the strong electrolytes. So these are things that ionize or dissociate fully. Ionize or dissociate. Giving ions. And these are strong conductors. Of electricity. What are some examples of strong conductors? Soluble salts. for example, NaCl. When I put NaCl in water, it 100% dissociates into the ions, and it conducts electricity really well. Any soluble salt, so let's say potassium iodide, and so on. Strong acids. These are molecular, but when you put them in water, they fully ionize 100%. There are 6 strong acids that you need to know of: HCl, HBr, HI. Then we have HNO3, HClO4, and then H2SO4. These are my 6 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. And then finally, strong bases. They also fully dissociate to give off ions, and they're strong conductors. Strong bases are group 1 and group 2 hydroxides. What does that mean? That means hydroxide ion bonded to a group 1 or group 2 metal. So for example, I guess I shouldn't have put this as my example. NaOH or CaOH2. So group 1 or group 2 hydroxides. These will conduct electricity very well. They dissociate or ionize completely or fully 100%. Now let's talk about weak electrolytes. So weak electrolytes partially ionize or dissociate, giving ions. So they do give ions in water, but not as much. And so these are somewhat conductive. We'll say poor conductors. They conduct, but not very well. What are the weak electrolytes? These would be insoluble or slightly soluble salts. So anything from the above table that was slightly soluble, something like AgCl, for example. That's not very soluble. So if you test it with a conductivity tester, the bulb will light up a little bit, but it's going to be pretty dim. Weak acids. For example, hydrofluoric acid. That's a weak acid, so it will only partially ionize in water. Acetic acid, all kinds of different acids. Any of the acids that are not these 6. Weak bases are also weak electrolytes. So any other bases than the ones we've mentioned here, group 1 and group 2 hydroxides. So for example, aluminum hydroxide. So if you see a hydroxide, that's not group 1 or group 2. Or ammonia, baking soda, and so on. So there's all kinds of weak bases. And then finally, we have non-electrolytes. These do not produce any ions whatsoever in water. So these do not produce any ions in water, and therefore they are non-conductors. They do not conduct at all. So what types of things would not give off any ions? These would be molecular substances. So they're covalently bonded. They don't have any ions to give off. So for example, Let's see, C4H10, this is butane. It's lighter fluid. Carbon dioxide, water, anything that is covalently bonded, that is molecular, is going to be a non-electrolyte, will not conduct electricity. So let's play strong, weak, or non-electrolyte. So how do you know? Well, you decide what kind of substance it is. You decide, is it molecular? If it's molecular, that means we know it's a non-electrolyte. Or is it an acid, base, or salt? If it's an acid or a base, you ask yourself, is it strong or weak? And if it's strong, then it's a strong electrolyte. If it's a weak acid or base, then it's a weak electrolyte. If it's a salt, meaning that it's ionic, like NaCl, for example, then you ask yourself, is it soluble or insoluble? If it's soluble, then it's going to be a strong electrolyte. If it's insoluble, that means it's going to be a weak electrolyte. So let's take a look at our substances here. So first you ask yourself, what type of substance is this? Is it acid, base, salt, or just a molecular? Well, this is covalently bonded. It's molecular, but it's an acid. And I know that because it starts with an H. So this is an acid. So then you ask yourself, is it a strong acid or a weak acid? And in this case, it is a strong acid. And so that means it's a strong electrolyte. I'm just going to write ELEC for electrolyte. Okay, next one. Next one is C2H6. What type of substance is it? This one would be molecular. It's covalently bonded, but it's not an acid. And so that means it's a non-electrolyte. Next one is KNO3. What type of substance is this one? This is ionic. It's a salt. And it is soluble. So it's a soluble salt. So that means it's going to be a strong electrolyte. Next one, NH4Cl. NH4Cl is also an ionic salt. It is soluble. So another soluble salt. And so that means it's going to be a strong electrolyte. How about the next one? C8H10N2. This is covalently bonded, so it's molecular. And so that tells us it's a non-electrolyte. And then the last one, MgS. MgS is ionic, but it is slightly soluble or insoluble. So that means that it's slightly soluble or insoluble salt. So that means that it's a weak electrolyte. So it conducts, but very, very little. All right. Last topic for today, as we're looking at some things to consider with chemical reactions here before we look at the types of reactions, is writing of different types of equations. So last year we learned about molecular, complete ionic, and the net ionic equations, and we learned about spectator ions to go along with that. Just so you know, a lot of times on the AP exam, they will specifically ask you for the net ionic equation. So you want to make sure that you practice how to write the net ionic equation. If it specifically tells you for the net ionic and you write a molecular, they will not give you the points for that. So be careful with the wording of the question, which one they're asking for. So let's try one here. We did these with mostly double replacement reactions, but we're also going to see an example of single replacement. So the first example we have here is potassium chromate and barium nitrate reacting together. So let's write those out. Potassium ion is K+, chromate ion is CrO4 2-. So potassium chromate is K2CrO4. We're reacting that with barium nitrate. Barium ion is Ba2+, nitrate is NO3-. So barium nitrate is BaNO3 They're going to react together. Remember when we talked about double replacement reactions, we said you put the two outer ones together and then you put the two middle ones together. So let's start with the two outer ones together. We have potassium ion we're going to put together with nitrate ion. And so that's going to be K plus and NO3 minus to make KNO3. We're not going to worry about how many there are because we're going to take care of that with balancing. And then you put the two middle ones together. So you have the chromate ion with the barium ion. Remember that the positive one comes first when you write out your formula. So barium chromate, 2 plus and 2 minus, so you just need one of each. So BaCrO4. And now we take care of all these subscripts and superscripts that are here by actually balancing it, not by using subscripts. So subscripts are used to write neutral compounds. The coefficients are used to balance. So looks like we need 2 of the potassium nitrates there. So this is my molecular equation, what we're used to. Next, we're going to write our net ionic equation, our complete ionic equation. And what that means is anything that is soluble in water, because double replacement reactions happen in water, when you put an ionic substance in water that is soluble, the ions dissociate, they separate physically. And so we need to show that. So this is soluble, so we write a little AQ next to it. This is also soluble, we write a little AQ next to it. This one, also soluble, we know potassium and nitrate salts are soluble, but this one is not soluble. And so we either put an S for a solid, or we put a downward arrow showing that it precipitates. And anything that is aqueous, like we said, we are going to show that dissociation of the ions. So the potassium chromate is made up of K pluses and CrO4 2 minuses. So we're going to write that out, K plus and CrO4 2 minus. But we need to show that we have 2 of the K pluses and 1 of the CrO2 4 minus. So what we do is we put the 2 there, not as a subscript, but as a coefficient. So 2 of the K pluses and 1 CrO4 2 minus. The reason why we write it that way is if you were to write like a formula unit of this, it would look like, you'd see, oops. You'd see a K plus, a CrO4 2 minus, and then another K plus, right? So 2 of the K pluses and then 1 CrO4 2 minus. All right, next one. This one is made up of barium ions and nitrate ions. So we need 1 barium ion, Ba2 plus. And then we need 2 of the nitrate ions, 2 of the NO3 minuses. On the product side, this one is soluble, so the ions associate as well. This is made up of K pluses and NO3 minuses. And since we have that 2, that means 2 of this whole thing. So that means 2 of the K pluses and 2 of the nitrates. And then we're going to write this as is because it's insoluble. It's a solid. It precipitates. So that means the barium and the chromate ions are just clumping together. There's no separation of these ions. So we write it as is. This is the complete ionic equation. Then we can write the net ionic equation. To write the net ionic equation, what you do is you cross out whatever you see on both sides that's the same. So we see 2 K pluses here. We can cross that out with 2 K pluses. We see 2 NO3 minuses and 2 NO3 minuses. So then we write whatever is left. So what we're left with is Ba2 plus CrO4 2 minus yields BaCrO4 solid. This is your net ionic equation. Now, out of habit, I always write the positive first before the negative. That's just how chemists write it. If you were to, write it as CrO4 2 minus plus Ba2 plus, you wouldn't have any points off. But just out of habit, it's more correct to write the positive one first, but, grade-wise, it would not make a difference. Now, the ones that we crossed out, the K pluses and the NO3 minuses, the nitrates and the potassium ions, these are spectator ions. So what does that mean? They sit there and they watch the reaction happen. They don't actually participate in the reaction happening. I do want to show you what this means here. So I'm going to try to draw my ions here. So initially we had potassium chromate, so K pluses, CrO4 2 minuses. And then we also had, what was the other one? Barium nitrate. So we had Ba2 pluses and NO3. So these were in solution, right? This is my initial solution. So my reactants here, I have this solution that has these ions, this solution that has these ions, so I mix them together, so I have all these ions swimming around in water, right? Now, what happens is, let's say the K plus and the Ba2 plus kind of get close together. What happens? Well, they're both positive, so they repel. How about these two, the chromate and the nitrate ions, when they get close together, they repel because they're both negative. Okay. What if the K plus and the chromate meet together? Well, they're going to attract, but that would be something that's soluble, so they're going to split up again. Same thing with the barium and the nitrate ions. If they meet up, they get close together, they attract, but then they make something that is soluble, so the water gets right in between them and separates them again. How about if the K plus and the NO3 minus meet up? Same thing. Opposite charges, they attract, but they make something that is soluble, so the water is able to get in between these ions and split them up again. But what if the barium and the chromate meet together? Well, those are opposite charges, they're going to attract, and in this case, once they attract, they clump together, and they make something that's insoluble, so the water can't split them up, and they clump down as a solid. And so at the end of your reaction, what you have here is the barium chromate solid. Just the ions are stuck together in the solid. The water can't get in between to separate the ions anymore. But you do still have the K pluses and the NO3 minus swimming around in the solution. So the reaction actually happened between the barium and the chromate ions. Those are the ones that are participating in the reaction. They actually changed. They went from the ions free-flowing to the solid. The K pluses and the NO3 minus were spectators. They're just there watching. They brought the ions that participated in the reaction to the reaction, but they were just watching. So they sat there swimming in the solution to start with, and they ended up swimming in the solution to start with. So that's why we call them spectator ions. All right. I do want to do one more reaction. Sorry, I'm having a hard time with this here. So this one is a single replacement reaction, if you remember. And so let's try this one to try to write the molecular complete ionic and non-ionic equations together. So we have lithium, Li, reacting with lead 2 nitrate, so Pb2 plus with NO3 minus, that makes PbNO3. NO3, 2. It's a single replacement reaction. If you remember, you look at the element, which is a metal, you compare it to the other metal, you see which one's more reactive. Lithium is more reactive. If it's more reactive, that means it's going to be in a compound, so it's going to come in, kick out the lead, so the lead is now by itself, and then form a compound between the lithium and the nitrate, so Li plus NO3 minus, so Li NO3. And then to balance it, you need a 2 here and a 2 here. So this is my molecular equation. To show the complete ionic, this is just lithium solid. It's not really made up of any ions. It's just neutral lithium, so I can't really do anything to it. I have to write it as is. This is an ionic compound that is soluble, so we can split it up into the ions, Pb2 plus and 2 NO3 minuses. On the other side, this is just lead, solid metallic piece of lead, and so there are no ions to dissociate here, so it's just Pb. And then this one is aqueous, so I can split it up, get 2 Li pluses and 2 NO3 minuses, and this is complete ionic. So now I can cross out whatever I see that's the same. I see 2 NO3 minuses here, and that is it. I can't cross this one out with this one because this is 2 Li, but this is 2 Li plus. Lithium ion is very different from neutral lithium. Same thing with the Pb2 plus and the Pb. This is neutral lead, but this is lead ion, so I cannot cross those out. So what I have left will be 2 Li plus Pb2 plus yields Pb plus 2 Li plus. And this is your net ionic. Your spectator here is the NO3 minus. Those are just kind of there to hold charge. They are the spectators just watching the reaction. So you can write net ionic for both double replacement and single replacement. Last thing I'm going to mention here is if you're asked for the net ionic, let's say, so you're looking for this reaction right here. You probably need to write the molecular first, this right here, but you might be able to skip the complete ionic. For some of you, you'll need to write out the complete ionic to be able to see what the net ionic is, but for some of you, you might be able to, once you see this, get to this right away. How would you do that? Well, if it's a double replacement and you're forming a precipitate, what you do is you write your precipitate as your product, so that goes in the products, and then you figure out what ions make this up. So the ions that make this up are Ba2 plus and CrO4 2 minus. So that's what you write in the reactants. So that's a little trick to go from molecular to net ionic with double replacement reactions. You just write what your solid is, and then on the other side you write what ions make up that solid. All right, that's it for this lesson. See you next time. Bye.